So the last part of this topic is sort of like the first part of this topic. If you remember, we started off looking at locus problems. Now we're back at looking at locus problems, but this time more specifically ones that arise from the parabola. Basically, we're going to get rid of the P's and Q's. So we're going to be dealing with parametrics, and we just want to get rid of the parameters. That's the idea. Eliminate the parameter. So it's always going to be find the locus of a particular point. So the first part of the question is going to be find the coordinates of the point you're talking about. Now once you've got those, now we're trying to find a relationship between the x and the y values. And that's what the locus is. Remember, it was a description on how y and x are related to each other. So this is where we'll get rid of the parameters. Now, it usually comes down to one of three cases. If it's the first case, then we're cheering because the answer's already been done for us. So if you look at the x value or the y value, and there's already no parameter there, you've got the answer already. So it'll just be x equals that, or y equals that. So if we ended up with p plus q for the x value, but negative 3 for the y value, there's no mention of a parameter in the y value. So the locus would be y equals negative 3. It doesn't matter what p and q are, y will always be negative 3. So that's probably the quickest of them all. The second one where there is an obvious relationship, so you probably only got one parameter. So say I ended up with 6t for the x value and t squared plus 1 for the y value. Alright, well I'll make t the subject of the first one, x on 6, sub it into the second one, and we've eliminated the parameter. So x squared on 36 plus 1 for this one. Then there's a third one. And the third one usually means some extra bit of working that we may have previously done. Some sort of link between the two parameters. So it usually involves more than one parameter. So you might end up with something like this. P squared plus q squared for the x value and p plus q for the y value. Now, it's too hard. You can't eliminate that. You need another relationship. So perhaps in this particular question, somewhere in the question we found a relationship that p times q was always equal to 3. That extra bit of information allows us to do something like this. Well, x is p squared plus q squared, which I could rewrite as p plus q all squared minus 2pq. But we know that y is p plus q, and we've found our relationship that pq is equal to 3, so we can substitute that in, and we get x equals y squared minus 6. The focal chord question that we looked at last week is an example of that. We needed the relationship pq equals negative 1 to prove that the point of intersection was always on the directrix. So alright, let's look at an HSC one. So way back in 2005. So a standard sort of question, we've got the points p and q given the standard parameters. X squared equals 4ay. They've told us the equation of the normal, so we don't have to derive that. So we've got it for both p and q. Now, the first part of this particular question that year said find the point of intersection of the two normals. I'm not going to worry about doing that now. We've done it before, but I'm more interested in getting to the locus part of the question. Part 2 then said, well, the equation of the chord, and again they gave us the equation, we didn't have to work that one out. But if PQ passes through node A, in other words it's a focal chord, so it's that proof of that PQ equals negative 1. Alright, so again I'm not going to do that because we did that previously with focal chord. So we've got our relationship PQ equals negative 1, but then comes the locus question. We're going to find the locus of R if PQ passes through node A. So because PQ passes through node A, we can use that extra relationship PQ equals negative 1. So X was equal to minus APQ P plus Q. But PQ is negative 1. So I can substitute that in, and I now get the P plus Q is X on A. Now the Y value. The y value was a outside of p squared plus pq plus q squared plus 2. Well, I'm going to rewrite that, again using the idea that p squared plus q squared is p plus q all squared minus 2pq, but then we're adding a pq, so we've got minus pq. Now the P plus Q, I can substitute in what we just did, the X on A. And the PQ, I can substitute in that relationship of -1. So subbing all that in, I no longer have any parameters. Remember, A is not a parameter, it was the constant for the focal length. So I can tidy that up, and I come up with an equation for the locus. X squared on A plus 3A. Let's try another one. So once again, our two standard points, P and Q, standard parabola. So the first part of this particular one, the equation of the tangents, and they gave us the equation, show that the tangents at P and Q meet at R with these coordinates. Well, again, we've done that before. I'm not going to worry about that now. More interested in what the coordinates are for the sake of this question. The second question, as P varies, the point Q is chosen so that angle POQ is always a right angle. So that bit of information will allow us to come up with a relationship between PQ. Find the locus of R. Right. POQ is a right angle, that's the key. Well, if that's true, the two slopes will multiply together to give -1. So working out the two slopes, tidying it up, we end up with, in this case, P times Q is -4. Alright, I now know PQ is -4. R is the point AP plus Q, APQ. But I notice I can get rid of it straight away just looking at the Y value. I don't need the X value for this question. Because as soon as I say PQ is -4, I've eliminated a parameter from either the X or the Y. Brilliant. There's my answer. Y equals -4A. So with our locus questions, we need to find coordinates of the point that we're looking for. Sometimes we have to find a relationship if we're using more than one parameters, and then use that to try and eliminate the parameters and come up with a Cartesian equation.